Hello, chemists! This is Ms. Placino, and you're watching lesson 9.3 on potential energy diagrams. In this lesson, we're going to talk about what information can be obtained from a potential energy diagram. Some goals for today's lesson. First and foremost, you'll be able to draw, label, and interpret PE diagrams. This is arguably the big one of today's lesson. You should be able to define exothermic and endothermic in relation to potential energy diagrams. And you should be able to use potential energy diagrams to calculate activation energy and enthalpy changes. So in this first slide, we've got a picture of a roller coaster, and you might be wondering to yourself, what does that have to do with a potential energy diagram? Well, you'll see, I promise. I'm guessing by now you've either had the opportunity to ride a roller coaster or at least kind of see one in action if, participating in this sort of thing isn't really your style. I want you to think back to that experience. Chances are you had to wait in some ridiculously long line so that you could just get on to the roller coaster. You sit down in that little car and you're either strapped down or strapped in, some sort of safety mechanism to keep you from flying out over the course of the ride. And then finally, the cars start to leave that little boarding area and the ride officially starts. What happens at the beginning of most roller coaster rides? Yeah, those of you who are kind of veterans of roller coaster rides know that almost all of them start by going up some gigantic hill. You've got a chain or a crank, some sort of mechanical power source dragging all the cars up to the top of the hill. What's happening to your anxiety levels as that's happening? Yeah, chances are they're starting to go up. Maybe you feel your heartbeat starting to increase. Maybe your palms are sweating. Maybe you are, anxious and excited all at the same time. Maybe you're questioning your decision to get on the stupid ride in the first place. Either way, the anxiety, the stress is starting to build. Eventually, you'll kind of get to the apex of that first hill. And this is kind of the point of no return. You are not going back. Once your little roller coaster car gets past the top, the rest of the ride is just going to take off and occur really, really quickly. And this is kind of what molecules experience in a potential energy diagram. So I want to think of roller coaster rides for molecules as being our PE diagrams. Now, I'm sure it goes without saying, molecules aren't waiting in line to participate. They don't have to worry about these loop-de-loops or anything crazy like that. And they definitely don't feel stressed the way that you and I do. But it's the same idea of going up the hill, going down the hill, and what's happening to their stability as this occurs. So let's go ahead and look at a PE diagram. This is a pretty typical looking one. We're going to see potential energy on the y-axis. We've got reaction progress on the x-axis. Sometimes you might just see time. It's kind of, one and the same. We've got our reactants over on the left-hand side of the diagram. We go up a hill, we come down the hill, and we reach the products. Really simple roller coaster ride. Along the way, we've got TS, E sub A, and delta H that we have to kind of familiarize ourselves with. So let's do that now. I want to start with activation energy, which is this E sub A term. Activation energy is the energy required to start a reaction. So basically, no matter what the reaction is, I generally have to put energy in to get it going. This is going to allow my reactant molecules to run into each other or collide with sufficient energy to start breaking bonds. You've got your reaction mixture and your reactants are constantly kind of bumping into one another, but it's not until they have enough energy where they're actually going to be able to eventually form the products. Activation energy is always a positive value. It's always energy being put into the system to initiate the reaction. Once activation energy has been put in and the molecules are colliding with sufficient energy, you could reach what's called the transition state, which is this T sub S, the top of the hill, and it's sometimes called the activated complex. So just get, kind of familiarized with hearing both of those terms. When you are at the transition state, you're at the highest point in the potential energy diagram. This is a very unstable intermediate. Just like you at the top of that hill on a roller coaster where you are very unstable. So here we have a situation where we're not really reactants anymore, but we also haven't formed the products either. It's very high energy, very short-lived, and we're starting to break the bonds of the reactants and form the bonds of the products. And really, once you've reached the transition state, you cannot stop the reaction at this point. Once the transition state forms, it will very quickly release energy and turn into the products. And finally, we have change in enthalpy, or this delta H term. Delta H, or the enthalpy change, is also called the heat of reaction. So just another couple of terms to familiarize yourself with. The delta H really just represents the difference in energy between the products and reactants. So if I was going to calculate delta H just from looking at a potential energy diagram, take the products minus the reactants, and that will be delta H. If we take a look at the example that we have here, the products have a lower potential energy than the reactants. So if I take products minus reactants, even without numbers here, hopefully it's pretty clear to see that delta H would be a negative number. Delta H can be positive or negative. The sign of delta H is really important as it's telling us what's happening with energy overall as we progress from reactants all the way over to products. So this is our very, very typical potential energy diagram. We start with reactants, we put energy in. We'll reach this high energy intermediate called the transition state. Once that forms, energy is released, and we're going to ultimately form our products. That's kind of the gist of it. So most of the potential energy diagrams that we look at are going to come in really one of two different potential layouts. The first is what we have been studying, which is for an exothermic reaction. Exo means out. So when an exothermic reaction occurs, they're going to release heat or energy out into the environment around them. Really important. If we were to calculate the delta H, and we kind of just mentally went through that in the previous slide, we'd see that the delta H, or the change in enthalpy from the reaction, is going to be negative because the products have less energy than the reactants. Every single exothermic reaction that takes place will have a negative delta H value. As a reaction like this occurs, an exothermic reaction, we would observe the temperature of the surroundings would increase. To give you an example, think about burning a sheet of paper. That is an exothermic reaction. The products have less energy than the reactants. As a result, energy or heat is released into the environment, and the immediate surroundings around the burning paper are going to get warmer. If I want to take this very generic looking chemical equation, A plus B is my reactants, yield AB, the product, and turn it into a thermochemical equation, I have to add heat or energy to either the products or the reactant side. In the case of an exothermic reaction, we know that energy is getting released. So that means that heat would be a product. I know we talked about this before, but we take our reactants, we put energy in to reach the transition state. Once the transition state forms, energy is released and the products will ultimately form. We can calculate delta H by taking the products minus the reactants. Okay. If we compare that to an endothermic reaction, it's a similar but different potential energy diagram. In an endothermic reaction, endo means in or inward. So endothermic reactions are going to absorb heat or energy from the environment. If we want to calculate delta H, now our products have more energy than our reactants. So we would calculate a positive value for delta H. And yes, all endothermic reactions have positive delta H values. As an endothermic reaction is taking place, the temperature of the surroundings will decrease. We know that energy gets absorbed as this type of reaction occurs. Well, where does it get that energy from? The immediate surroundings. If you have ever had a chemical ice pack before, you've got kind of this crunchy feeling substance in a bag. It's ammonium chloride. And you've got this little bubble thing that you have to pop. And that bubble just contains water. The ammonium chloride is going to dissociate or break up into ions. And that process requires energy. So we're going to suck in or absorb energy from the atmosphere, and that's going to make the chemical ice pack get cold. So this process, dissociation, requires energy. So these surroundings will provide that energy, and it will feel like things are getting colder. So since energy is absorbed in this case, kind of going towards our system, we would put heat on the reactant side of our thermochemical equation. Although our PE diagram does look a little different, it's the same idea. Energy is absorbed as we go from reactants up to the transition state, and the transition state is the highest point of our potential energy diagram. Once the transition state forms, energy is going to be released, and ultimately we will form the products. All right, let's do some practice with this concept. I think I'm going to skip over some of these early questions on potential energy diagrams that just kind of have you, looking at like the anatomy of a PE diagram for 1 and 2, and then putting some numbers to a potential energy diagram for 3 through 14. I want to focus on what I think are some of the more involved questions, something like question 15. For each equation, draw a potential energy diagram and label. So that means reactants, products, delta H, T sub S, and E sub A. I've noticed in my years of teaching, most students want to skip this part for whatever reason, drawing the PE diagram, but that's really the key to being able to answer these sorts of questions. So let's see, zoom in on number 15 a little. So we've got a chemical equation between nitrogen and hydrogen reacting to form ammonia. Let's go ahead and get that balanced. Hopefully you're thinking 1 in front of the nitrogen, 3 in front of the hydrogen, and 2 in front of the ammonia. You don't really need the balanced chemical equation to deal with thermochemistry, at least not this aspect of it, but it's good practice. In addition to seeing ammonia as the product, we also see 92 kilojoules of energy as a product. What type of reaction has occurred, endothermic or exothermic? Let's see, we've got 92 kilojoules getting produced. Energy has leaving the system. It's being released. So this must be an exothermic reaction. So I'm going to draw just a really generic looking PE diagram for an exothermic reaction. Easy enough. Let's start labeling of my reactants, my products. I know the transition state is going to be the highest part of the graph, the plots. I know that activation energy is the energy from the reactants to the top of the hill. And I know that the delta H is going to be the difference between the products and the reactants. Okay, so let's put our PE diagram to work. First question, if the E sub A, the activation energy of the forward reaction, is 15 kilojoules, what is the activation energy of the reverse reaction? Okay, well, let's start figuring this out. Activation energy of the forward reaction is 15 kilojoules. So the activation of the reverse reaction has to be from products all the way up to the top of the hill. I know that this little part of the diagram is 15 kilojoules. And I know that delta H is going to be 92 kilojoules. I'm not going to worry about the sign here because if I'm going in the forward direction, it's exothermic, so it would be negative. And this is asking about the reverse reaction. So when it's from products basically back to reactants, it's going to be positive. So I know activation energy now. Sometimes you'll see it as like EA prime. Activation energy of the reverse reaction is going to be from products to the top of the hill. So it's as easy as just adding them together. And you should come up with 107 kilojoules. All right, if the reactants have a potential energy of 1,000 kilojoules, what is the PE of the products? So I'm going to label 1,000 kilojoules at my reactants. I know my products have to have less energy than that as they're lower in the potential energy diagram. Well, how much lower? We know that delta H, the difference between products and reactants, is 92. So how do you think you'd figure this out? Yeah, we just take 1,000 minus 92, and we'll come up with 908 kilojoules. You can imagine if you took away the potential energy diagram, suddenly these two questions become a lot more difficult to answer. So if you've got a question referring to a PE diagram, always take the time to draw it out. It only takes a couple of seconds, and it will save you a lot of time and frustration in the long run. All right. As always, I would encourage you to go back, work on these practice problems, check your answer, make sure you're feeling confident about your ability to solve these types of problems. That's going to wrap it up for today, chemists. Thank you so much for tuning in, and I hope you found this helpful.